Okay, so let's continue. So last time we derived the electron-phonon renormalized phonon propagator, which is given by this kind of bubble, and you sum over all infinite number of such bubbles, and you get a renormalized phonon propagator, which is a double wavy line here. Capital italic D is the propagator of the renormalized phonon, which is given by this expression in relation to this bare phonon propagator, capital D0, and also this, this bubble diagram, electron-phonon mediated, say, a bubble. But there's one remark I need to make right now. So remember, this point that I mentioned last time is to be the renormalized electron-phonon coupling. However, in such a renormalized phonon propagator, this kind of derivation, we simply just use the bare electron-phonon coupling constant, m0, but we will later on renormalize this electron-phonon coupling constant later, right? So this is something that I didn't mention last time. So the way to renormalize this electron-phonon coupling constant m0 is the same procedure that we screen the Coulomb potential, right? So we can take the same way that we screen the Coulomb potential by this electron hole bubble, and here we could sort of renormalize this m0 electron-phonon coupling by inserting this electron hole bubble in there. So you could sort of insert one bubble which connect to this bare phonon propagator. You know this. These two are the M point electron propagator. All right. So if you consider the stuff just in between these two electron propagators on the right and this bare phonon propagator on the left, and those stuff in between is nothing but this Coulomb screening bubble, right? So as a result, we could consider not just one bubble corrections, but many bubbles. Say we can insert this vertex point, there's two bubbles and three bubbles and up to n bubbles, and n goes to infinity, and we could sum over all such electron hole bubbles, and also this this Coulomb potential in between those electron hole bubbles. So, and if you just use the mathematical expression to sum up all the diagrams here, this is nothing but m0 out front, multiply the whole thing in the bracket, where the first term in the bracket is 1, which represents this bare electron-phonon coupling. The second term corresponds to this single bubble insertion, which gives you this g square, where little g represents the electron propagator, and u0, where u0 is Coulomb potential. And then the second diagram, non-trivial diagram, represents the second bubble insertion, which is this one. Okay, so you repeat this procedure up to infinite number of electron hole bubble, and also u0 propagator. So as a result, you could simply sum over all this geometric series, and you get exactly the same dielectric function that you are familiar with when we screen this Coulomb potential. So the renormalized electron-phonon coupling M as function of Q is given by M0, which is a bare electron-phonon coupling, divided by this dielectric function. So remember, we have the similar relations. The screened Coulomb potential U effective is given by u0 divided by epsilon, right? So same thing happens here, that we could renormalize electron-phonon coupling by inserting this electron hole pair bubble and this Coulomb interaction in between. Okay. So then, because we already renormalize this m0 to n, as a result, in this phonon propagator calculation, we simply just don't renormalize this m0. Otherwise, we may have a double counting, and that's why in this renormalized phonon propagator, it involves only this m0 right here. But we will renormalize M0 later, okay, which is right here. All right, so a second remark regarding to the renormalized phonon frequency little omega as function of momentum q, which is this expression right here that we derived last time. So remember, it's capital omega is the phonon frequency in this very naive Galilean approximation, which corresponds to this constant, the Einstein frequency, and but we will renormalize it by this, again, epsilon dielectric function. So, but we are interested in this low energy, long wavelength limit of this phonon frequency, which plays an important role at low temperatures. Okay, so therefore we could just take advantage of this RPA that we studied already in the Thomas Fermi part, that we take this long wavelength q goes to 0 limits and this epsilon RPA in the static and long wavelength limit. Static means omega vanishes and q goes 0 limit. It is given by k Thomas Fermi square divided by q square. Okay, so I believe you have checked that. This is one of your homework. And for three-dimensional electron gas, you can show very easily that this is k Thomas Fermi square is given by this quantity here. So 4 times Fermi momentum kf divided by pi times the Bohr radius A0. So now we could simply just plug in this static and long wavelength limit of this epsilon RPA to the renormalized phonon frequency in the same limit, which is given by this capital omega divided by square root of the epsilon. And you know very well that this epsilon in the static and long wavelength limit is given by a square of the k Thomas Fermi divided by q squared. So you take square root of this and you get this linear in q relation that we already pointed out last time. Okay, but what we didn't do is to really estimate this prefactor, this coefficient in front of the linear in q relation of this renormalized phonon frequency, and you could take advantage of your, say, free electron gas model in this three-dimensional Fermi sphere, and you could easily use this relation for the free electron gas model and plug that in, and you could see that this is the final expression. And this is nothing but this acoustic phonon mode, and I assigned this to you as a homework exercise to really derive this prefactor correctly. Here's capital M refers to the ion mass, and little m the electron mass, and z is the charge of this system and the ions, and a factor of 3 may come from this factor of 3 here. Okay, so you could very easily compare this to the gallium very naive constant frequency to the acoustic phonon that you already renormalized, and you have figured out that the magnitude of this frequency renormalized phonon is significantly reduced by that factor, okay, and also by a linear in Q factor. So if you make a plot of this, later we'll see that the real part of this effective interactions, electron-electron interactions, mediated by the electron phonon, and you will see that a shift of your frequency is that this electron effective interactions become 0. Okay, so we will do that later, but you will see immediately that this little omega as function of q, when q goes to 0, is actually significantly smaller than this constant capital omega. So you can consider this capital omega as some kind of optical phonon mode, right? So because this is somewhere here, which is a constant independent of q, but you then move this optical phonon constant frequency to acoustic mode. Okay, so this is just a simple analogy. I'm not saying that this is exactly the optical phonon mode, but this is the only frequency that you obtained, right? At the bare level, when we consider no lattice, a gallium model, but the gallium model is normalized to a physical acoustic phonon mode, which really linearly proportional to Q. Okay, so, but in that case, we simply just take advantage of this screening of a Coulomb potential by this dielectric function, epsilon. Remember, this epsilon serves as a kind of a screening of a long-range Coulomb potential, and without the screening, we only get a constant phonon frequency, but with the screening of electron-electron interactions, the phonon frequency gets renormalized to this acoustic phonon, okay? Which means that we need to consider a short-ranged Coulomb repulsion between electrons to correctly reproduce this phonon frequency, acoustic phonon mode. So, and this is an important point that a realistic solid-state system, the Coulomb interaction is always short-range, okay? As a result, if you're trying to figure out this phonon frequency which couple to the electron, okay, and then this phonon must actually reproduces this linear in Q behavior, which is a low-energy acoustic phonon mode, okay? And the reason why this is acoustic is precisely because this either electron-electron Coulomb interaction or the ion-ion Coulomb interactions are short-ranged. Okay, so they are screened. As a result, you will get this acoustic phonon mode. Okay, so let me just make a contact to the first approach to get acoustic phonon mode. Remember, we could consider a simple harmonic oscillator like this with a potential which is nearest neighbor type, right? Suppose we have such a simple harmonic oscillator of atoms along the chain, and we could second quantize this, and we get a phonon mode, and exactly we could recover this acoustic. And now you know the reason why we get acoustic, because here in this harmonic oscillator chain problem, we only consider a nearest neighbor. So the nearest neighbor interaction between the atom along the chain really mimics this short-range screamed Coulomb potential. Of course, this screamed Coulomb potential is not exactly the same as this nearest neighbor interacting, say, harmonic oscillator along the chain, but in spirit, we only consider nearest neighbor potential or nearest neighbor interaction between the two ions. That should be sufficient to reproduce this acoustic phonon mode. Okay, so in a way that these two approaches are more or less equivalent in spirit, quantitatively speaking, they could get the same feature. Of course, quantitatively speaking, you don't get exactly the same prefactor right here, but I think physics is the same, right? So you either consider nearest neighbor coupled harmonic oscillator along the chain, or you consider a Coulomb screen potential when you calculate this phonon frequency. Okay, so I think this is a second remark I would like to make to actually link everything that you have learned. Okay, so I think so far everything is consistent.
Sorry. Of course, this link I think quite interesting, but another thing is that I am the one ion in a three-dimensional system. So it means that there is a two optical mode and one acoustic mode. So it means the mode, even though considered screening, the mode will degenerate. Also, the polarization direction will also different.
Yeah, of course. To really reproduce the 6, say, phonon modes, you need to consider a real lattice. Okay, but that is another story. Okay, so you could again do this on the lattice. It is, I think, manageable. All right, so if you calculate this kind of a bubble diagram on the lattice, you may be able to. I didn't do that, but you could try. Okay, so if you do everything on the lattice, on three-dimensional lattice, I guarantee that you'll recover everything that you learned in solid state 1. Okay, so we didn't put it on the lattice. Okay, so but if you do, then same thing here. So if you consider a three-dimensional coupled harmonic oscillator, and you'll get how many modes? 6 modes, right? Okay, so there's really no inconsistency, no contradiction, nothing. Everything is consistent, okay, and understandable. So let me just go on. You could sum up total effective electron-electron interactions by combining both the Coulomb interaction and the electron-electron interaction mediated by electron-phonon. So as I mentioned last time, the electron-phonon mediated electron-electron interaction can go negative, can go attractive, and the magnitude of the attraction really overcompensate the magnitude of repulsion. As a result, the total effective electron-electron interactions is really attractive, okay, and low temperature limit, and this is the source of a Cooper pair and the superconductivity in ordinary metals, and this is what we will do right now. Okay, so the U effective is the sum of these two. This U term, capital U term, represents this Coulomb potential, and this capital M squared times this italic capital D is the electron-phonon mediated electron-electron interactions. Okay, so diagrammatically you could use this kind of cartoon picture to represent such two terms. So I use double dash line or dot lines to represent this Coulomb screened effective Coulomb potential, and a double wavy line for the renormalized phonon propagator, and this kind of electron-phonon coupling constant has been renormalized to renormalized value capital N here and there. So in other words, we need to really sum up these two terms. Okay, so what do we do? So you simply just add these two. So these two interactions, our two diagrams, fully renormalized. Here's a little Q0 represent this frequency. It could be in real frequency or multiplier frequency. Good. So now we could really make a plot of this, the whole thing, right? So let's take a short break. When we come back, we will make a plot of this total effective electron-electron interactions as function of, say, frequency Q0, and then we'll see that when this frequency is actually smaller than some critical value, which is given by this renormalized phonon frequency here. Suppose my external frequency, or Q0, is less than this omega of Q, so you immediately see that this term becomes negative, right? Which means that when the external frequency or energy that you put into your system is very, very small, or you don't put any external energy in your system, which means that Q0 equals 0. When Q0 vanishes, of course this term becomes negative. And this is the only place that you can have negative sign, because all the other terms are positive. This M0 square, magnitude square is a positive, epsilon square is positive plus, and U0 is positive, epsilon Q is positive. Everything is positive except this denominator. Okay, so this is this physics that drives the whole thing negative. All right, so let's take a short break and we'll make a plot of this, the real part of this U effective. Of course, it can have imaginary part because this is renormalized photon propagator, which contains both real and imaginary part. Okay, so but I think this real part dominates the size of the effective electron-electron interaction. Okay, so let's take a short break.
Excuse me. Your Q0 is a kind of an external frequency, right?
Yes.
So I mean the epsilon, that is the function of Q0 of both of the Q and Q.
But remember, we're using RPA. Okay, and the static limit, omega goes to 0. Of course, you can put this back. Okay, so let's look at this plot. So these two plots are the electron-electron interaction mediated by electron-phonon coupling, and we know very well from just the previous, what I said previously, that the only thing that could drive the total effective electron-electron interaction attractive is the electron-phonon mediated electron-electron part, right? So this is the reason why I only plot this phonon contributed electron-electron effective interaction. And if I apply the real part of this U electron phonon effective versus omega, where omega is the external frequency. So you can see that for this normalized interaction, electron-electron mediated by electron phonon, you can see that this yellow shaded region are all negative because this real part of U effective electron phonon drops to negative values, where omega is larger than omega of q, you get this positive value of effective electron-electron interactions mediated by phonon, and the saturation value when omega goes to infinity or very, very large, this corresponds to this RPA of this effective electrons mediated by phonon. And by comparison, you could also make a plot of this, the same thing, except now I just plot the real part of the bare electron-electron mediated by electron phonon. And by bare, I mean this phonon frequency is unrenormalized. So this is the bare phonon frequency. So again, you have this similar feature, except now this capital omega is much larger than this small omega of q, and also the interaction strength between electrons mediated by electron phonon in the saturation limits is actually much larger than this renormalized value, which is what we expect, because remember this U effective in the Coulomb part is actually U0 divided by epsilon, right? So this U effective interaction between electrons mediated by phonon is what? Is proportional to m0 squared divided by epsilon squared. Okay, as a result, without the screening effect, this saturation value, this RPA limit for this U effective is much larger than the renormalized one. Qualitative this feature between these two are the same, right? So in other words, if your external frequency is smaller than some critical value, which is your phonon frequency, then this effective electron-electron interaction mediated by phonon becomes attractive. Okay, but this renormalized version should be more accurate. Okay, so now let's look at this expression of this U effective mediated by electron phonon, which is, okay, so this Q0 here is really the same as this little omega over there. So this is the full expression of this U effective mediated by electron phonon, and we could re-express the denominator and numerator in such a way that we could recognize this more straightforwardly and more intuitively. So which means that we could take advantage of the gallium relation. So this is the relation when we talk about the gallium approximation. And so we could use that to simplify the expression. Okay, so remember the normalized photon frequency omega q squared is given by this gallium frequency capital omega squared divided by this epsilon. Okay, so then we take this static and long wavelength limit to simplify this even further. So we get this, and this GEP is what we call the electron-phonon coupling constant. Okay, so later on we will just use this simplified version of this effective electron-electron interactions mediated by phonon, and we call this coupling constant GEP, which is given by this value right there. Right, and then we could simply just look at this renormalized, say, electron-electron interaction as a function of Q and omega 0. And you could very clearly see that when Q0 is very, very small compared to omega of Q, and this whole term change signs to a negative value. Okay, so now we could consider the attraction between electrons, because the size of the magnitude of the negative value of this phonon-mediated electron-electron attraction overcompensate this positive repulsive Coulomb interaction. But before we go on to describe such an attraction between electrons, and let me just make a final remark regarding the phonon self-energy coming from this electron-phonon coupling. Remember, this electron-phonon coupling renormalizes both the electron propagator and also phonon propagator. So in terms of phonon propagator, this kind of bubble diagram will normalize this phonon energy, and as a result you get phonon self-energy. But precisely the same self-energy is actually correcting this electron propagator. So if you consider an electron propagator, you could have such a electron phonon, right? So this is self-energy correction to electron propagator, again contributed from the electron-phonon coupling. So either way, so electron-phonon coupling will normalize this, both propagators. So you could consider this D inverse or G inverse. Okay, so both sigma E or sigma phonon contains both real and imaginary part. Especially the imaginary part of the self-energy in general does not vanish. Okay, so this, as I mentioned already previously, that the imaginary part of the self-energy represents some kind of dissipation or decay in time in this correlation function. So if you calculate this, say, phonon self-energy coming from electron-phonon coupling, and especially the imaginary part of this, and you'll find that this is given by some finite value in the low temperature limit, and which we call this as attenuation coefficient, gamma. Okay, so we know very well that this phonon propagates like a sound wave propagation, okay, because longitudinal phonon mode is actually this kind of oscillation in space, that you have oscillations of a high density of ions and also low density of ions, and this high and low density of ion really oscillate in an alternate fashion, and the sound wave like phonon propagation propagates along the same direction that those momentum goes. Okay, so this kind of phonon propagation is really similar to what the sound propagates. Okay, when the sound propagates, remember the molecules that in the air that propagate exactly this fashion. Okay, so you have a high density of air molecules and low density molecules. They oscillate in such a way that this sound velocity goes along the same direction as those molecules oscillates. All right. So, but we know that the imaginary part of the self-energy really makes such a quasi-particle decay, right? And so, if you calculate phonon Green's functions, like this, okay, and you could compute this, real-time correlation functions of the phonon mode, and if you have such an imaginary part of the self-energy of a phonon propagator, then immediately you will get decay in time, something like this. So in other words, the phonon propagator gets decayed, and the decay constant is defined precisely by gamma, which we call this attenuation coefficient, or attenuation of sound ultrasonic attenuation coefficient. Okay, so which means that this, the sound-like propagation of the phonon modes will decay in time. Okay, because the presence of a finite imaginary part of a self-energy. Okay, so let's take a short break. When we come back, I will make another final comment on the so-called Coulomb anomaly in the solid state, which arises precisely because of the electron-phonon coupling. And the Coulomb anomaly appears when this momentum of electrons on the opposite sides of the Fermi surface exchange a phonon. And you get some kind of a singularity in their dispersion when this momentum transfer is about 2 kF. So it's called a 2 kF anomaly or a Coulomb anomaly. And we will review that because most of this phenomena has been discussed in this advanced solid state 1. Okay, so let's take a short break. Okay, so let's just make a final two remarks regarding electron-phonon coupling. As I mentioned, this imaginary part of the phonon self-energy will lead to the decay of a phonon propagator, and also this so-called attenuations of sound propagation. Okay. Another important physics is related to the so-called Coulomb anomaly, which happens when this phonon momentum reaches around 2 times kF, where kF is the Fermi momentum. So because of electron-phonon coupling, this is a cartoon picture of what this happens. This means that these electrons across this Fermi surface on 2 opposite sides of the Fermi surface may interact with phonon. Okay, so when that happens, those electrons very close to the Fermi surface on the opposite 2 sides carry almost the opposite momentum. One is kF, another is minus kF. So when they interact, the momentum transfer is precisely 2 kF. So which means that at low temperature, those electrons, active electrons, are circling around the Fermi surface, and so the opposite side of the electrons at Fermi surface may exchange momentum and couple to phonons, and when that happens, the phonon momentum is precisely 2 kF. And so when that happens, both electron band and also phonon band will show some anomaly, which means that there's some singularities happens in their spectrum. For example, if you look at the electron dispersion for free electron, we get a perfect quadratic band, right? So this, which is a k squared. But because of this phonon coupled to electrons, so near this Fermi surface, 2 sides of the Fermi surface, you get very sharp slope change of your dispersion, and this comes precisely because of the singularities of this, again, the phonon band, right? So the phonon band, if you calculate frequency of a phonon due to electron-phonon corrections, and this is given by the bare phonon term times the square root of this stuff, which comes from the self-energy of this electron-phonon coupling, and this eta was defined earlier when we defined this sound attenuation coefficient, and this h function is given by this complicated log plus 1, and when this x, which is defined as k over 2kf, reaches 1, then you get a very sharp slope. So if you take the first derivative of this omega phonon respect to momentum, you get this this log function. So especially the denominator of the log is 2kf minus k. So when k is very close to kf, you get finite number divided by 0, and you take the log. So log 0 is actually infinity. So you got infinity in this phonon dispersion. So because of this same thing, same physics occurs if you examine this electron dispersion. Okay, so the same divergence occurs both in the electron dispersion and also in the phonon band. Okay, so in other words, when k goes to kf, you get very singular, sharp, kind of a singular slope change in both spectrons. And this is what we call this Kuhn anomaly, which was first discussed by Kuhn long time ago. And this phenomena has been observed in solid state already. So the final remark is about the vortex correction. So this is the electron-phonon coupling diagrams, and the vortex correction is defined by this diagram, where you simply just coupled electron-phonon coupling in a way that they form a connected vortex, and this is up to cubic terms in this coupling constant, right? So if you multiply this electron-phonon coupling term in Hamiltonian 3 times, and you can form such a diagram. But then this Mid-Gauss theorem tells us that you don't need to worry about this vortex correction, because he showed that this vortex correction is actually proportional to the square root of electron mass divided by the ion mass times this bare electron-phonon coupling constant. So we know that this electron mass is 1,000 times smaller than this ion mass, right? So you take square roots, it's still an order of, say, a few percentage. So this kind of few percentage correction, this compared to 1, is nothing. So you can forget about this vortex correction completely. So that's good, because now we have only sub-energy corrections and no vortex correction, and we are ready to discuss this attraction between electrons due to electron-phonon. So the effective Hamiltonian for this attractive electron-electron interaction has this form. Okay, so this is before we actually consider this effective electron-electron interaction. So this is just electron-phonon coupling, right? So you have this conduction electron kinetic energy, and you have a renormalized phonon and also renormalized electron-phonon. Okay, so that's about it. And but now we will start from this effective Hamiltonian for electron and phonon coupled system, and we will discuss so-called Cooper instability, which is the instability towards the Cooper pair formation, where these 2 electrons can actually form a pair, and we will discuss how that happens and why this happens based on this effective Hamiltonian. And when we discuss this Cooper instability, we will examine this similar so-called ladder diagram that we discussed already in this Anderson localization problem. Remember, in the Anderson localization problem, we discussed the vortex correction, right, or electron backscattering processes by impurities, and here we will study very similar physics, namely this electron-electron backscattering by this effective interactions, which is attractive interaction. Okay, so let's take a short break. Okay, so let's officially start the last chapter of this course, which is about the BCS theory of superconductivity in ordinary metals. As I mentioned, the effective electron-electron interaction mediated by electron-phonon coupling can go attractive at a low temperature limit, and a cartoon picture to illustrate this kind of a Cooper pairing between two electrons is this, that there are two electrons, but they see this phonon vibration on the lattice. So because of the phonon coupled to electrons and these two electrons feel attraction between them, as a result they form this composite particle called Cooper pair. So the previous semester we have mentioned this phenomenology of the ordinary superconductors, namely this kind of antiparallel spins between these two electrons when they form Cooper pairs. That is because of this Pauli principle, and also the center of mass momentum is actually 0. So that is because we should follow this canonical momentum for this whole object. And then this canonical momentum of this whole thing, and also the London equation, requires that this two momentum exactly get cancelled. And well, I won't repeat that, but you could check our earlier notes previous semester. Okay, and the most important phenomenology of the superconductors is the Meissner effect, right? So in the superconducting state, the system is a perfect diamagnet because the magnetic flux cannot penetrate into this superconductor because there is a repulsion of the external magnetic flux that you insert when this material is in the superconducting state, and this is called the Meissner effect. And the Meissner effect comes from the London equation that you could derive in a semi-classical way. So again, those are the phenomenology, but I'm saying that because of this Meissner effect, the London equation, also Pauli principle, and this canonical momentum of this Cooper pair, and we see that these two electrons must cancel their momentum and also their spins. And so it's called S-wave singlet pairing of these ordinary metals when they are in the superconducting state. So, but we take this for granted. Okay, so but now let's look at how that happens from the more, say, fundamental level, meaning from this kind of so-called particle-particle channel of electron scattering by this kind of effective attractive interactions between them. Okay, so as I mentioned, at low temperatures, the most active electrons are around this Fermi sphere or Fermi surface, and for metal, the opposite side of the Fermi surface, or these two electrons living across this Fermi sphere, they may form a Cooper pair, and their spins must be antiparallel to each other. So, but why does it happen? Why does this pairing occur? So we could look at this diagram right here and calculate these contributions of this so-called particle-particle channel of electron scattering when they have this effective attraction. Okay, so this diagram illustrates that there are two electrons carrying momentum k and minus k. So they interact by this attraction. U effective, you could consider just a single dash line or multiple dash lines. You could just sum over all possible such a so-called ladder diagram, and then you can solve this so-called Peter-Solve beta equation self-consistently, and you will find that this diagram, when you sum up all this kind of ladder diagrams, it is divergent. Okay, so especially when this kind of momentum transfer between these two electrons is very, very small. So you can imagine that there is a momentum transfer between this plus k electrons and minus k electrons, okay, a slightly momentum transfer. But this momentum transfer is really, really tiny. Of course, we can consider a large momentum transfer diagram, but they won't contribute a singular divergence. So the most singular part of this diagram comes from the limit when q is very, really small. It means that there are almost exactly two sides of the Fermi surface carrying exactly plus and minus kf, and they have almost no momentum transfer, and temperature is low enough, and in such case these two electrons form Cooper pairs, and as a result this kind of a diagram diverges. Okay, so this there is a one-to-one correspondence between this kind of a cartoon picture and the divergence or singularities of this Cooper instability diagram. But we could take advantage of the Green's function that we learned today and to really calculate this instability. So this instability tells us that these two electrons carrying opposite momentum, opposite spin, they like to interact by this attractive interactions, and which means that at lower temperature, these two electrons will actually form a pair at ground state. And so let's just examine this diagram, because we know how to compute this ladder diagram already. So remember, this U effective is attractive interaction, because we already sum up this Coulomb repulsion and attractive electron-electron mediated by phonon. So this is a net effective electron-electron interactions, and this carries a minus sign. Okay, so see how important this minus sign is to make this diagram divergent. Okay, so let's consider this kind of diagram, and we call this ladder diagram T, and this T shows a ladder structures, and the simplest possible ladder is just a single dash line. But I suppose that we have such a scattering between two electrons, and we consider that two electrons actually get destroyed altogether right here when they interact by these attractive effective interactions. And then they actually are created, two new electrons are created carrying different momentum, k prime plus q and minus k. And this q is what I mentioned, this momentum transfer, which is between k and k prime, the difference. And then remember, this is precisely this kind of backscattering that we discussed in the Anderson localization problem, because you simultaneously destroy two electrons carrying opposite momentum almost. Okay, so it's not a particle Hall diagram. Also, it is very important point to make that this you destroyed electron carrying a minus k is not the same thing that you create an electron with momentum in other direction. So in the second quantized fields representation, this is C minus k, but this one is actually C dagger of k. So you don't simply just try to reverse the direction of electron propagation and call that this is again an electron-hole pair. So it's not electron-hole pair. As I mentioned, these two particles are destroyed at the same time simultaneously, while this electron-hole pair is this kind of diagram that you destroyed one electron but you create another one. So remember, this is C dagger C, while this one is actually C dagger C dagger. So I suppose that this is a very important distinction between a particle-particle channel and a particle-Hall channel. So you could also imagine that these two electrons are destroyed where they carry different momentum, say K1 and K2, and K2 is not necessarily minus K1. It's the same thing. So this is the simplest possible one leg ladder, and you could add one more ladder of the same type. So let me just, and so on and so forth. So let's just look at some of all such ladder diagrams and how and why this diagram diverges. So the first diagram with just one dash line represents just the single U effective contribution. So this is just a single U, but the second one shows internal structures circled by red, where you need to sum of all the internal degrees of freedom, remember that, which includes what? These two dash lines and two solid lines. So let's do it. So you could show by plugging this kind of electron creation and destruction operator of this diagram, and you could do this weak contraction. So when you do the weak contraction, because this is the particle-particle channel where this electron is created along this direction, the same directions, so this diagram carries the electron minus sign. This minus sign here because this is a particle-particle channel. Okay, so when you perform this weak contraction, you really need to move this operator around to actually contract them and to form this Green's function. Right? So when you do so, since they are fermions, they should obey the anti-commutation rules. And compared to the electron hole bubble, this particle-particle channel relative to this particle-hole channel carries the extra minus sign. So let's just sum over internal decreased freedom. So you got two effective U right here carrying different momentum, k minus k1 and k1 minus k prime, and two bare electron propagator, little g here. So let me just write down the next diagram. Okay, so then I just stop here, okay, because you could very easily generalize this to many ladder diagrams. So now we could formulate kind of a recursive relation for this diagram we will try to sum over, and this is called the vertex function, or recursive relations for this vortex function. So let me just define this as a vertex function. So at bare level, this vortex function is given by just U effective, remember. But beyond this bare level, you get some contributions of this 2-leg and 3-leg and multiple leg diagrams. But there is a relation between left-hand side of a renormalized vortex function and right-hand side. Because right-hand side, it is also kind of an infinite number of ladders hidden there. So we could just express this in a more transparent way. And this is called the integral equation. Some people call this Bethe-Salpeter equation. So if I use this circle inserted here, and I could represent this renormalized vortex function, which is complicated black box in between these 4 electron lines, right? And 2 incoming electrons carry k plus q and minus k, and when they get scattered, they become k prime plus q and minus k prime. And remember, this k and k prime are both close to the Fermi momentum. So this renormalized vortex function could be considered as a single dotted line plus an infinite number of ladders. So you can simply just consider the second diagram in the middle, and this could be cut into 2 parts. One is a single dashed line, but the remaining parts could be infinite number of dashed lines, right? Okay, in general. So for example, this one, suppose I have infinite number of dashed lines. I can simply just cut this diagram into 2 parts. One is the single dashed line, which is precisely this one, and the remaining part is a ladder diagram with how many ladders? Well, infinity minus 1. This is infinity minus 1 and plus 1. So infinity is infinity minus 1 plus 1. But infinity minus 1 is still infinity. Is that so funny? So this part of the diagram contains, again, infinite number of dashed lines, which is, again, the same thing that's on the left-hand side. So this is exactly the same thing. So if I simply just redraw the plot, which I will use the same size and same number of dashed lines. So this is T on the left-hand side, but what about the right-hand side here? Still the same T. So this is the coupled equation or recursive integral equation, which means that this unknown vertex function on the left-hand side is a function of a unknown vertex function on the right-hand side. So both sides of the equation contains the same unknown vortex function to be solved. And this is the typical equation called integral equation. Okay, so but we need to solve this in order to get this T. So remember, we need to argue and show that T goes to infinity when temperature is really, really low. Okay, so how do we do that? So let me just formulate this integral equation symbolically. And so T, K, K prime, Q. Okay, so this is the integral equation that we need to solve. And of course, in general, there is no exact solutions of this equation because this U effective is a really complicated function of Q, right? So in general, you can do it only on a computer. But fortunately, we could make further assumptions to simplify this calculation, especially this U take a very simple form, which is the S wave of interaction, which is independent of omega. And independent of momentum. So this is called S wave. Scattering, meaning if this effective U is independent of frequency and momentum around the Fermi surface, then we can just consider this just a constant. If this is just a constant and this little g is the bare electron Green's function, then we could exactly solve this integral equation. And this is what we will do next time. Okay, so time is up. We could complete this calculation next time.